The first presentation is by Yanis about erosion, and the second is by Theo, who is sitting there, about plant residue management, and the third is by we have a Finnish speaker, a presenter actually from the Finnish Environment Institute, who will talk about gypsum application in Finland, and then the fourth, and then we. If we have time, we will have a coffee break for 15 minutes. And then the fourth presentation is by Isabel, who will talk about the nutrient balances and carbon in a long-term field experiment. I guess that's the experiment at Abswal. And then we have another presentation from Randy Froses. And she's presenting online about nitrogen and mitigation measures for nitrogen losses. And in the last, I would also take the opportunity to introduce a new EU project that NIBIO is leading together with actually Østfold County is also involved, and also some other Norwegian partners. Yeah, so Yanis. Yes, welcome, please.
Thank you, John. Try this microphone. Yeah, sorry, we couldn't get the presentation mode on, so I tried as well during the lunch, so I had to give up. Anyhow, well, let's say congratulations with the World Soil Day. I just went into my emails and I get an enormous amount of congratulations from all over the world with the World Soil Day, but it is a bit of a strange day. I'm from the Netherlands. It's the 5th of December. That's our Sinterklaas. So St. Nicholas is going around in the Netherlands at the moment, sharing all presents with all the kids in the whole country. Impressed by this man. Okay, but I will tell you something about reducing erosion with start at the source. I had a different title. It was just soil erosion, but John said, well, that's boring. Can you not make it a bit better? So I tried to get a bit of a different perspective. And then when you talk about sources, erosion is, let's say, the enemy of soil erosion is water or wind. I focus on water because it's a soil day today. I focus on water and try to explain a bit on what is ongoing in terms of processes with water erosion. And of course, another source of erosion is the victim, the soil. I will not tell too much about it. Only at the end of my presentation, I will have something to tell about that as well. To put it a bit in perspective, how does that work in Norwegian circumstances? We have in our institute a program which is called the Soil and Water Monitoring Program. And that is monitoring for more than 30 years already the discharge of agricultural driven catchments in Norway. And I calculated for two fields, the Skutri and the Murder area, the amount of soil loss per decar or per hectare if you want, from this area as an average of 10 years monitoring. And so that is from Murder, it's 2 ton per hectare, and for Skutri 1.5 ton per hectare about. What is it then? It doesn't sound so much, but this is the number of lorry truckloads that are leaving those two catchments every year. So polluting the water bodies with all the sediments and the attached nutrients with that. Just to give a bit of a national overview, this is from the same program, but from a bit more areas, and this is a bit of an old calculation. It's done by my colleague Stephen Corner, and you can see there is a large deviation of parts. You go from 70 kilograms per hectare to 2.8 tons per hectare from those different areas, totally dependent on soil type, on climate, and on land use, especially land use. The percentages that are standing behind these that was the use of this study, is to show how much of the soil loss is done in winter period, or let's say the melting period. So 47% means that from November to April, 47% losses of soil in that period. Just to highlight the bit of a typical Norwegian circumstance with a good winter and a lot of soil loss in winter. So when we talk about soil processes, we want to look at what is actually ongoing. And we normally start looking at the rain episodes in a catchment. What happens with the rain when it enters your catchment or when it falls on the ground? Well, you get something which is called splash detachment. The raindrop, the individual raindrop has a power to loosen soil and to even transport soil when it touches your surface. When you go a bit further and water starts to flow, you will get something which is called sheet erosion. So the water drops that fall on your surface start to flow over when there is saturation or when the intensity is too high. There, sheet erosion can produce already detachment as well, flow detachment of your soil. Even further, more concentrated flows, you'll start to find a phenomenon which is more or less called rill erosion. And in these pictures, you can see how they look like. They are small incisions in your field, in your agricultural field. And then even further, even more concentrated, you get these gully erosions. Gully erosions are separated in two different types. You have the permanent incisions and you have the ephemeral gullies. The ephemeral gullies is on the left side of on the right side. No, how are you looking? On the right side. This is in Krokstad, close to this area, where you can see a nice gully developed also in the spring period. And this is the area that I partly used in my PhD. This is China, the left plateau of China, where you can see big gully systems that are permanent in the landscape. So that's the deviation between the two types of gullies. Normally, we don't see too many permanent gullies in Norway. We had them in this ravine landscape, but they are leveled out. Well, not all of them, but some of them. So, bit of a summary. Starts to rain, you get splash erosion. Starts to run over your surface, you get sheet rill erosion, and it concentrates even more, you get gully erosion. Then for simplicity, I'm forgetting all the other erosion phenomena that are there. You also have stream bank erosion, you have tillage erosion, and you have something which is called creep erosion, where basically your whole field on a longer time series moves towards the stream. Those phenomena I'm not going to talk about here. But they are, of course, of interest as well for your soil loss in the landscape. It's a pity that we don't have the animation now here. So now it immediately pops up what's going on. Let's talk about the water again, because water is the driving force of the soil. We already started with the splash erosion, with the raindrop, and then it started to flow. If you are upstreams, or if you are at the start of your flow, you will see a quantity of your water or a volume of 1 to 2 bottles per second that runs over your surface. If it starts to concentrate a bit more downslope, it goes from 10 to 1,000 bottles. And if you even go further, and this is at the end of one of the Juve catchments, then that is about a 5 square kilometer catchment. Then you go even to more than 1,000 bottles. In terms of soil erosion, or in terms of measures, what we should try to do is to capture the water here, to avoid that this amount of water runs over your surface. The focus should be on measures upstreams in the catchment, because that is the amount of water you still can handle. Then, of course, the question is, what kind of measures can we have? This was also a very nice animation. Erik, you have to fix it. So you have your landscape, back to our landscape again, and you will get an episode, either a snow melt or rain episode or whatever, and you will get problems due to those, the erosion or even downstreams, the flooding areas. What is then possible in terms of your management, your land management, your area management in your landscape? Well, there are an enormous amount of possibilities, but basically I will show you some of those in a picture that can help reducing soil erosion. And the whole background of this is, and I mentioned water as being the enemy of soil for soil erosion, but if you can't beat them, join them. And that is basically what you have to do. You have to try to capture your water in your landscape to avoid too much water flowing downwards, flowing out of your area. So if you start at normally those agricultural driven catchments in Norway, upstreams is more forested areas, then you get your agricultural area. So if you start upstreams, you can try to capture your soil or your water as long as possible in the forested area or in your peat area or whatever, it's upstreams there. You can use these dams. We have several examples of those in Czechia, in the UK. You can use retention ponds. This is an example in Norway. One of the farmers built it himself or digged it himself because he had problems with overland flow that was downstreams of his forest. And then when it starts to run over your soil, you should try to or increase your infiltration. This is experiment from Till. By using cash crops, deep rooting cash crops to open them up your compacted layer. Or you can try to reduce the speed of the water by grass strips or other barriers in your landscape. And then more downstreams will go to the stream itself, stream bank erosion, but also using vegetation to also reduce the speed of the water so that in the end you will have a kind of a lower peak flow due to all these kind of resistant measures in your landscape. Good. I have no idea about time, so I will just try to wrap up a bit. So we have the water, which we saw as an enemy, but basically you can use the water as well. You can try to capture it. You can try to reuse it even. We have several projects ongoing now where you try to combine both the flood reduction measures and the drought measures. If you capture the water for a long period, you will also reduce drought risk. But what you should do is look at basically the victim of this is your soil. And then we already heard a lot this morning about soil health, which is luckily the trigger for the politics to have focus on soil. Finally, I've been working on 35 years in soil science, but finally the politics also sees this as a problem, which is good for us. Thank you, Baran. So we are now focusing more and more on how can we treat our soil to indeed increase infiltration or to indeed produce more food or whatever soil function or ecosystem service you want to connect to that. And especially in Norway, and Baran also showed this already in his presentation, our focus is on organic matter, soil structure, compaction, and that causes increase or decrease erosion rates. So if we are able to fix the structure and to reduce compaction and to increase organic matter, we have solved a lot of the erosion problems as well in Norway. So this again, this is still working on this experiment, and this is from the same period as I showed my previous picture with gullies in the landscape. reflecting the problem. So someone else, is that, yeah, there is something new. That is, it's not too known yet. And again, pity that the animation doesn't work. Healthy soil, and you don't see this one yet. This is work from my PhD student, Frederik Beuye. He asked ChatGPT to draw a healthy soil. And it's fine. I mean, yes, you can recognize them, you can see the biology in your soil, you can see deep rooting plants. There is a lot of things ongoing that you can relate to in terms of, yes, this is a healthy soil. But then he made the same question, can you also make a bad soil or an unhealthy soil? And then ChatGPT came with this. And to be honest, I don't see too much of a difference between the two. It still looks healthy. The only thing is that there is a bit of a water layer in here. So there's a bit of a stagnation of your water, apparently. Which shows that even ChatGPT doesn't know anything about soil and the status of soil. Which means that we have not done enough research yet. Because ChatGPT gets its knowledge from the research or from the publications or from everything that's on the internet. There is not enough information available yet to give you a good picture of what is an unhealthy soil, what is a bad soil. Although even the new report from the GRC, the status of soil in Europe, claim that 60% of the soils in Europe is in a bad state. But ChatGPT is not convinced yet. So that's an application we have to do to feed this kind of information needed for politics, for whatever, with the status of soil. Also in Norway, because Ola was mentioning this morning already that we don't know if the soils are bad in Norway or not, or if they are good or not. We have no overview. So Teresa will solve that for us with our monitoring program. Thank you.
We'll see about that. Hi, my name is Till, and it's really nice to be here today, to be part of this celebration for the World Soil Day. And I chose quite a long title for my presentation. But this should not scare you, because it will be interesting. I promise. So the title is Effect of Different Types of Soil Tillage on Straw Incorporation and Decomposition. And I will talk about possibilities and challenges under practical conditions. Yeah. As I think everybody knows that soil tillage is one of the most important field operations. Soil tillage is important to incorporate weeds. It's important to it's important to incorporate plant residue. It's important to fight weeds and to facilitate high yields of good quality. But soil tillage, especially plowing, is also energy intensive and labor intensive, so it's costly. So there's an interest in reducing the soil tillage intensity, both in order to take care of the soil structure, but also to save energy and costs. At the same time, in Norway, with the climate change, it will be wetter conditions, increasing precipitation. And that means that there will be a limited amount of days workable for field work. So we need a higher efficiency to be able to explore the workable conditions. And there is a need, and we have heard about this earlier, there's a need to keep the soil covered. We have also new, stricter environmental rules that engage farmers, that force farmers to reduce soil tillage intensity and keep plant residue. And this may, under practical conditions, be a challenge, because it is expected that we need at least 30% residue cover to reduce erosion. And trials have shown that straw residue may hamper plant establishment and thereby reduce yields. So this can be in conflict with the aim of increasing food production. So in EBIO, we have done quite some tillage trials in the recent years. This picture is from a project Forest, where we tried different types of soil tillage to establish autumn cereals. So we have included plowing, we have included reduced soil tillage, direct drilling, but also a new method, strip till. It is known that in case of direct drilling, that plant residue, that straw may be a problem. So we wanted to try this. It's not a new method, but in Norway it's not tried yet. So we want to include this type of strip till, which is based on the idea that it's actually a combination of direct drilling and reduced soil tillage. And it's based on the idea that there's a strip that is tilled, where the seed is put into, while the rest is left undisturbed. So you need a greater road distance to do so. But by that, you can reduce the interference of residue and seed plant. So this method is used quite a lot in North America and Canada. It's used more and more in Germany, but it hasn't been tried in field trials in Norway. So this is quite exciting. This picture shows the soil surface after direct drilling, where the seed is drilled directly into the plant residue. And the picture shows that if we do direct drilling, we get a quite rough soil surface. And this is the consequence of both standing stubble, residue lying on the soil surface, and quite large aggregates created by the machine. And as Jannis was talking about, the energy of the raindrops. And by having the plant residue on the soil surface, by having quite a rough soil surface, we may reduce the risk for erosion and we may improve infiltration. But one question is about the seedbed quality, about the temperature and the moisture conditions in the seedbed. And the other challenge is the risk that the plant residue is in conflict with the seed. So I think there's no doubt that plant residue, that straw is a resource. Plant residue is a resource to reduce erosion, as we have heard about. But plant residue is also a resource when it comes to organic carbon, as we heard earlier today. So under practical conditions, we would like to keep the straw as long as it is useful for us, but we would like to get rid of it before it can become a problem. So the question under practical conditions is how to do so. And as I said, we have done quite some research on that. And this figure shows you the results from a tillage study. So we have three different types of, I have to go there just to see my own figure. So we have three different types of soil tillage in autumn. We have plowing, we have harrowing, and we have no soil tillage, both combined with a shallow stubble cultivation in advance and without. Here you see the amount, the percentage of residue cover, and the black line is the 30% that is needed, that is expected to be needed to reduce erosion. When you see the figure, you see the more intensive the soil tillage, the less straw residue on the soil surface. But at least in our trials, the only way to obtain 30% coverage was to do no autumn tillage at all. So all residue left on the soil surface until the year after. So question then is, what happens to the plant residue that is not on the soil surface? So we dig the soil profile, and we use the frame with a 5 times 5 centimeter raster, and counted the amount of straw on the different layers. So the darker the color, the more straw it was in the different places. In the first line, you find plowing, harrowing, and no tillage. So plowing is efficient to bury the straw, while harrowing leaves more straw on the soil surface and mixes the soil and the straw residue in a better way. No tillage, all residue kept on the soil surface. While if we combine it with a shallow stubble cultivation, we get a better mixture of soil and residue. Interesting, although stubble cultivation only was done with 6 centimeters working depth, so quite shallow, we got a really good mixture of soil and straw residue and a good reduction of the amount of straw residue on the soil surface. And how straw residue and soil are mixed is important for the decomposition of the straw. So in this figure, in this part of the trial, we use litter bags. So in this figure, you find days after harvest, and you find the residual amount of organic matter in these litter bags. Here is the different types of soil tillage without stubble cultivation, while here it's the same type of soil tillage with stubble cultivation. And when we take a look at this, we see that in case of stubble cultivation, which was done directly after harvesting, decomposition of the straw starts already early in autumn. While in case of no stubble cultivation, nothing happens to the straw until it is incorporated into the soil. We take a look in spring, we see that all measures where the straw is incorporated are more or less efficient to get decomposition of the straw. While if all residue is left on the soil surface, nothing will happen to the straw. So all the straw will still be on the soil surface in spring, which then leads to a higher demand for body seeding technique and agronomy. So in this picture, we see autumn cereals that were established in autumn 2022, and where it's direct drilling, and we had problems with the distribution of the straw. So here we see that already, that even if there has gone a year, it's still a lot of not decomposed straw residue on the soil surface. And that may create problems later. So the next slides I want to show are from a cooperation we had with the plant health department, where we checked the effects of both soil tillage and straw residue on the amount of weeds, which is in this figure here. In this figure, we have reduced soil tillage, spring versus autumn. We have plowing, spring versus autumn. We did that for 2 different years, and we did that without straw and with straw. And the different colors are the different types of weed. So if we start with the effect of the tillage, we see that in case of plowing, there was in case of plowing, we managed to reduce the amount of weeds by approximately 50%. If we take a look at the timing for the soil tillage, in case of reduced soil tillage, tillage in autumn was much more effective to reduce the amount of weeds than reduced soil tillage in spring was. In case of plowing, there was not really a big difference. So in case of plowing, the timing was not important. If we take a look at the type of weeds, it was mostly Poa annua we found. If we take a look at the effect of the straw residue, maybe not surprising, but taking away the straw led to more weeds. And this figure shows the amount of Fusarium DNA in the cereal samples and the amount of mycotoxin built up by these by the Fusarium. So Fusarium is, without me being an expert on plant health, Fusarium is a serious disease which leads to that if there are mycotoxina in the cereals, that the cereals can't be used neither as feed nor as food. Again, it's the different type of soil tillage. It's the harrowing spring versus autumn, and it's plowing spring versus autumn, two different places. So we see that in case of plowing, Fusarium DNA was reduced by 30 to 75% in the samples taken. We take a look at the timing for soil tillage. We see that in solar at the one side, tillage in autumn was more efficient. There was found less Fusarium DNA when tilled in autumn compared to tilled in spring, while we found the opposite effect on the other side. When it comes to the effect of the straw residue, in this trial, we didn't find any significant effect of the straw residue on the Fusarium. But other, also Norwegian studies show that Fusarium can survive on the straw residue, and that straw residue may be an important inoculum source. If you are interested in this type of trial, it is published. It is published international, but also Norwegian.
1 minute.
Perfect. Because now I want to conclude. If I manage. Would be better in presentation models. Okay. I think I was mentioning that before, that there's an increasing interest in reduced soil tillage, but also in keeping the soil covered. In the latest research, we found that reduced soil tillage can give as good yields as plowing, so that is promising. In our trials, we found that the effect of plowing was independent on both timing and depth. So it was no difference if we plowed in autumn or in spring. And by reducing the plowing depth, we may save both soil structure and considerable amounts of diesel. So in many cases, we can reduce the plowing depth. We tried 25 versus 15 centimeters. If a straw coverage of 30% coverage is requested, there shouldn't be done any kind of autumn tillage. In our trials, double cultivation was effective to incorporate the straw residue. It was actually as efficient as plowing and harrowing was, but it's a less intensive interruption of the soil structure, and it has a lower fuel consumption. In our trials, when we did stubble cultivation, decomposition of the straw started already in autumn, and that reduced the demand for intensive soil tillage in spring. But there are still open questions, actually a lot of questions. And we got even new questions by doing this research. And one of the questions is that we found the yield reduction after stubble cultivation, which may have an interaction with the nitrogen and the nitrogen availability. Another interesting question is if we do stubble cultivation and all the straws incorporated in the upper 6 centimeters, it's still good visible, but it will be less than 30% coverage. And if even straw that is in the upper soil layer can have effect against erosion. And of course, the weed discussion. Because if we talk about minimum tillage, it's often the discussion about Roundup or not. And all these questions, this topic is far too interesting to press it into a 15 minutes presentation. So that is why I want to sell the report that we have written for a bit more than a year ago about plant residue and how these could be explored better. So you can find it on the internet and you can download it from the internet if you are interested. So I know I have used my time. So thank you.
Okay. Hello and greetings from Helsinki. My name is Petri Ekholm and I work at the Finnish Environment Institute, and I have been working quite a lot with the Finnish gypsum amendment of agricultural fields. And in Finland, the problem is agricultural phosphorus loading. We have tried different kind of measures to reduce the loading, and we have perhaps succeeded a little, but we still need to cut the phosphorus load to the rivers, lakes and coastal waters to meet the water quality, meet better water quality requirements. And erosion is very strong thing in Finland, and I guess it's also in Norway. You can see here a flat field with a very, very high erosion, very turbid water coming out of the flat field. And satellite also sees from it. In the left photograph, you can see a part of the archipelago sea and estuary, which then shows a lot of soil particles making the water turbid in that area. And very briefly, what is the gypsum amendment we have done in Finland? We have found out that it's the most cost-effective method to reduce phosphorus load. These are a little bit old prices, but we have calculated that it's about 60 euros per removed kilogram of phosphorus. And in catchment scale studies, we have found impressive reductions, even as high as 72% in particulate phosphorus, also in dissolved phosphorus, not always, but sometimes very good performance. And then as a bonus effect, we have found decrease in dissolved organic carbon. And this gypsum effect lasts about from less than 3 years to about 5 years, in some cases even a little bit more. And what is good in the method is that it's suitable for large field areas, especially fine textured soils, but we are also testing it now in other kind of soils for its performance. And it doesn't hamper the farming practices. And when we have asked farmers' experiences, they have mainly been neutral or positive. And we haven't found any negative effect on the quality or quantity of yields. By turn, in contrast, the gypsum contains a lot of calcium and sulfur, so there is a lot of useful nutrients in it. And according to some perhaps subjective views, also the soil quality may improve. We have also tested all kinds of things. For example, we have found out that it doesn't cause any harm for riverine biota and soil microorganisms. And here you can see the astonishingly clear water right after the gypsum treatment. Usually, as you saw, our runoff waters are very, very turbid, but after gypsum treatment, they are also almost miraculously clear. So the effect is immediate. Well, there are different types of gypsum, and in Finland we use that phosphogypsum. You perhaps know that there's an apatite mine in Siilinjärvi, Finland, which is owned by Norwegians. We were not very clever to sell it to you. And then that apatite there is dissolved with sulfuric acid, which forms then orthophosphoric acid, which will be used for fertilizers, and lots of gypsum. In that area, they call it Alps, the hill, which is made of gypsum. And the gypsum there is magmatic apatite, so it's free from cadmium and radioactivity. But there is also in sedimentary apatite in other countries, which is not so good. This is so-called phosphogypsum, but there are other gypsum forms also. Flue gas desulfurization gypsum, mined gypsum, and recycled gypsum. Here you can see the trend how the gypsum amended field area has increased in Finland. It all started somewhere around 2008, when there was a period of about 10 years of lab field and catchment scale studies, mainly conducted on clay areas. And the results were so promising that 2020 started a nationally funded gypsum project, which gives gypsum free for farmers. It's just they only have to give a license that it can be spread on their fields. Otherwise, it's totally free for them. And thanks to that gypsum project, we have now amended about 80,000 hectares, and the goal is still much higher. And in that map, you can see the areas which belong to this gypsum project. How does gypsum works? Well, it's much more soluble than lime, and so it will be dissolved quite fastly in wet soil to calcium and sulfate ions, which then increases the ionic strength of soil solution. When that ionic strength increases, the electrical double layer around the particles becomes thinner, which allows them to come closer and form microaggregates, possibly stabilized by calcium bridges, and they are then less prone to erosion. In addition, phosphate will be adsorbed a little bit more strongly to the particles, being still available to plants, but not so easily flushed with rainwater. And as a bonus effect, organic carbon losses decrease, but gypsum has no effect on pH. Then what happens to calcium and sulfate? Sulfate will not be bound by soil particles under finished conditions, but calcium will part, and some of the calcium bound by soil particles will then cause an extra release of magnesium and possibly potassium. What we have also analyzed plants, and we also only see a temporary increase in sulfur concentration. There is a decrease in selenium, but it's also a temporary. And for surface soil, we see an increase in sulfur and electrical conductivity, but nothing more. And the result is that runoff carries less phosphorus and organic carbon, but more sulfate, calcium, and magnesium to waters. This I don't go through, but I just show that there are a lot of studies performed in Finland, and these are the publications written in other languages than Finnish. There are some Swedish, for example. Well, gypsum is not an every place solution. Major restriction is lakes. When a farmer wishes to have gypsum on his or her fields, he or she looks at the map. If the fields drain into a lake, that means no gypsum. But if the fields drain into the sea without lakes in the transport, so that is eligible for gypsum. And what we wish to avoid is sulfate-mediated eutrophication of fresh waters, which may cause that phosphate from sediments will be released strongly than without that sulfate-mediated eutrophication. It has to do with dissimilatory sulfate reduction and reactions with iron and sulfate. Then there are some other restrictions. If the soil are low in magnesium or potassium, then no gypsum, but you can decide that based on agronomic soil tests. In Finland, we are not allowed to use it on groundwater areas, although a moderate increase in sulfate is totally harmless to humans and structures. We don't use it in nature conservation areas. And if you cultivate plants very sensitive to salt, then perhaps avoid gypsum. And selenium in crops decreases at first, but it can then be accounted by giving selenium to animals in fodder. So now we are exporting this idea to other countries. We are now working on an Interreg Baltic Sea region, Kyprek, which has Sweden, Latvia, Lithuania, Poland, and Åland Islands from Finland, teamed up to study whether gypsum works outside Finland. And then there is a sister project, Nordgypsum, which also includes Nibio and Aarhus University. From Nibio, we have been collaborating, for example, with Dominika Kreminska and Ian Liu. And right now, just an example, for example, in Poland, there might be 3 million hectares gypsum eligible fields, making 8% of the country's area, and Swedish data shows the same percentual share. And we are hoping that we get something like that also from Norway. But right at this moment, there are lab studies going on at the Aarhus University, which include 2 samples from Norway. They will do under the supervision of Cosin Hegrath leaching experiments with gypsum, structuralime, and structuralime amended soils. Of course, we have controls, and we study also water holding capacity, clay mineralogy, clay dispersion, aggregate stability, and a new method for me, drop cone method. We already know that clay dispersion seems to reveal whether a soil is sensitive to gypsum, but aggregate stability doesn't show anything, at least according to preliminary results. Well, then the question, gypsum amendment of agricultural fields applied in Finland, but not in Norway. Very few details in this table. We see that in Finland and Norway, agricultural phosphorus losses may be very high. Both countries have clayey soils. Is there some difference between soil chemistry or physics? Perhaps. Both countries are lands or lakes, and whether there is some other factors. Why it's not used in Norway, I leave the question to you. And while thinking about the question, you may look at our websites or read our brochures. And then we also have in YouTube an animation which is in Norwegian. Probably you don't hear this voice now. I forgot to put that on the voice, but if you go to YouTube and write gypsum Norwegian, so I hope you will find this animation. Well, thank you for your attention.
Thank you very much. It's my pleasure to be presenting some of the data from outdoor soil, where we look at nutrient balance and a lot of other things in the soil. But before I talk about that, I couldn't resist adding a small slide this morning because we're talking a lot about sampling methods and living labs. And I just wanted to advertise this internally funded project that we have right now, where we are looking at, we visited carbon agro farmers, so farmers that are trying to do new things using conservation agriculture in Norway. And what we did here is that we visited them, but we also found their neighbors and asked if we could take samples there. So we do this comparative study right now where we look at soil carbon, clay content, we sample soil density, so exactly what we discussed this morning, how important it is to look at. We look at 4 different methods of aggregate stability. We're checking microbial activity, and very importantly, we're also archiving samples so we can go back after a few years, because some of these farmers have only just quite recently started. And the way we sampled it, we did it in a grid, which is about the size of pixels of Sentinel satellites. And we can also use remote sensing to connect our data to other data sets. I'm not going to talk about it more. I just wanted to advertise it because I'm going to hopefully be sending out a report by the end of this year about a lot of these results, and maybe also present the data hopefully next year, just so you know. If you're interested in hearing more, just talk to me afterwards. So, but now let's talk about runoff. The apple soil experiment was started in 1988, and it's quite some time ago. So why are we doing this? The experiment was started to have a better understanding of how we can balance the demands of food security and environmental or nutrient loss to the environment. And this was part of the time when there was the Mjøsaksjon, whereas they're trying to reduce the loss of phosphorus to the freshwater system. So if you here see, that's approximately where our soil is. The water that is lost from agriculture goes into the Mjøsa, or into the freshwater system. So because it's, so this is the phosphorus future particularly abound. So this is sort of the short range consequences that freshwater systems near agricultural fields get issued with eutrophications there. But now we all know that we have the Oslofjord problematic, and this is also what this experiment is trying to understand. How can we produce food in a way that we don't have those nitrogen losses into the marine system? So that's long, it's dissolved, so there we have long range transport. And how do we do this? So this setup was designed many, many years ago. So the data I'm presenting is not my own. I'm lucky that there are people before me that did all the work. It's set up in a way that we have 12 mini farms with 4 fields in each mini farm that have a 4-year crop rotation. And we're testing 6 different cropping systems. So we have 2 replicates of each. And this is a system has been changed a lot after 2020. So I'm going to talk about data before 2020. And at that point, we had 3 conventional systems and 3 different organic systems. And how do we measure the runoff? So we measure surface runoff from each of the farms, but then we also measure the drainage water from each of the fields to the farms. So then we have, that means it's 48 fields where we measure runoff in these tipping buckets where we get the volume of water, and then we take nutrient samples once a month so we know what the nutrient losses are. You can see a sort of a depiction of what it looks like. Today, I'm going to only talk about the drainage water. I'm not going to talk about surface runoff because we have much less detailed information there. I'm going to talk a lot about what's happening at the field crop level, and there we only have very detailed information for the drainage water. So if you see phosphorus levels that are way lower than you're used to, that's because we're talking about drainage water and not the surface runoff. So the 3 cropping systems I want to concentrate on for this today is that we have a reference system, something we call an optimized system, and then we have a grassland system, which has been managed under organic premises. The reference system is one that's run pretty much typical for 1980s agriculture, which means that we have autumn plowing, we have mineral fertilizer that's only given in the spring in 1 dose, and we don't use any cover crops. And very importantly also, which I didn't write down, that the straw is removed from the system. Whereas the other system, the optimized system, it's qualifies quite well under the realms of conservation agriculture, which means that we have only spring harrowing. Mineral fertilizer is given in a split dose, so depending on the growing season, and then cover crops are there. And very importantly, the straw is not removed. And then as a contrasting system, I want to include something that's quite different, which is a grassland system, where you have 3 years of, so you have only spring plowing for the barley. That is a grassland system, and cow manure is given in amounts that are harvested from the system. So none of these 2 systems have external inputs of organic fertilizer. The thing that's given to the grassland system is based on how much is removed from the grass, and it's calculated on how many cows this sustains and how much manure goes back. We can talk about you see that the 2 conventional systems have exactly the same crop rotation, only that we have the cover crops in addition for the optimized system. Also very importantly, notice potato is in both, and they're managed quite similarly. So you still have soil working to get the potatoes in and out of the field for the optimized system. Whereas in the grassland system, we have 3 years of grass lay and then 1 year of barley, for which it gets plowed. So this is not a long-term grassland. So this is still a managed grassland system for production. So what are our questions here? And there's a lot of things we can ask, but I wanted to talk a little bit about the runoff. So how much are we losing per system? But very importantly also, which are the crops where we're losing most? And then personally, I think it's more important, we also look at the efficiency and the environmental costs. So if we lose a lot, is it because we're adding a lot of fertilizer, for example, or is it something else that's happening? So how much of the fertilizer we add we're actually using, or environmental cost, how much of the fruit we produce, how much out of the harvest, how much we're losing to runoff. So this is just one way to look at it. I'm going to try to link some of this also to soil properties and looking at where are the phosphorus and nitrogen dynamics differently, because there's some things we should understand. So this is just a timeline of the nitrogen runoff. So again, this is just the drainage water. And you can see quite a clear trend here that the reference system there's a lot of fluctuation. That's the first thing. It's important that we have these long time series because you see there's a lot of fluctuation. But we see generally that the reference system is losing most nitrogen, followed by the optimized system, and then we have the grassland system at the bottom. We can also look at this in terms of, this is very just simple box plots. It's a lot of variations. So I just chosen to show box plots instead of trying to do some averages because it's a little misleading. But here we can see exactly the same trend. This is just summarizing the data, but this is only from 2013 because this is the years we also have the crop-specific information. So for the nitrogen, it's actually quite similar, whereas for the phosphorus, we can see there's a difference. There, the reference system is really popping up as the one that has the highest losses, whereas the optimized system actually is lying much lower. So this is this part. So I took away all the explanations, also I saved it like a separate slide, so it's a little confusing for me. But so you hear, again, this is like the first part where I did see it. We see different dynamics of nitrogen and phosphorus, the way these systems are managed. So now I want to show you a little bit when we look at the crop level to understand where some of these differences lie. So now splitting it up into separate crops, we can see that there is generally the highest losses again for the reference system, but we see that for the optimized system, there's sort of a twofold division. We have two crops that are losing quite a lot of nitrogen, and then two that are lower. So now the question is this because they get less fertilizer, or is it because the cover crops are working better there because it's the third and the fourth year after the potato year? So in theory, cover crop establishment is much better. So there could be different ways on why this is lower, and we're trying to understand a little bit more how this, why this is. For phosphorus, we can see generally that it's much more flat. So nitrogen can see that there's quite a bit of variation between the crops between the years, whereas for phosphorus, this trend is not as much fluctuating. And this is very important when we think about managing our soils. So you can see that, for example, for potato, it's high for both the reference and the optimized system and the nitrogen, whereas for the optimized system, we see this drop, that it's much less loss of phosphorus from this system. So what we do throughout the year with those 3 other years of not plowing, having cover crops, does something to the potato year that is in the long term stabilizing it. Yeah, so let's think a little bit about nitrogen efficiency. So what I did here is I tried to calculate a little bit on, okay, about how much of what we give as a fertilizer is lost, to understand a little bit more. Is it because we give more that we lose more? Is it because we don't use the nitrogen well that is coming in? So just to it's easier to understand, low numbers in this case is good because it's more efficient, and high numbers is bad. Here we can see that the reference system and the optimized system actually move a little bit closer to each other. So the difference is not as much anymore. This is because the reference system has been getting some slightly higher fertilizer amounts. You can also see that wheat is suddenly much closer to the level of oat and barley. Remember, before it's quite a bit higher, which means that wheat, the cover crops in wheat probably are actually working quite well, but there's a limit on how much. If you give more, at some point you can also lose more of the nitrogen. But we see that it's in a way just as efficient. And then here we can also see quite a big difference between the grass and the barley year, which means just changing your system. It is an organic system. It's quite little impact on the system in the terms of plowing and everything, but just changing the way we fertilize and we have a crop that's different from the grass, the efficiency drops dramatically from year to year. And this is again important for management when we're thinking about nitrogen losses to Oslofjorden or any marine system, that you have to be active every year, actively doing the right things to minimize runoff. You also see that the fluctuation is very high, and that's because we're dealing with manure. And then if the timing is a little off and you're a little unlucky with the rain, losses can be quite high from year to year. It's great for getting our organic material, carbon into the soil, but there's a high risk associated with it. So now let's look at, this is not all of the environmental costs, obviously, but it's one way to look at environmental costs, and this is comparing how much of what we get harvested, what is the proportion of what we get harvested is runoff in that system. Again, low number is good, high number is bad. And here you can see again, things are actually moving a little bit more closer to each other. So what stands out is that we have a lower grass system. It's much lower losses, or like the efficiency is very high. Then like we have low environmental costs, but we can't eat grass. So there's ways to calculate how much grass cows can feed and how much milk we can get. I made it a little simpler. So okay, if we go up one trophic level, you usually lose 90%. So we keep 10% of the energy, which then would move the grass efficiency or the environmental cost to a higher level. The other place you might say, well, we shouldn't have potatoes. Like the cost, the environmental cost in this case of potatoes is much higher. But then again, potatoes are a very useful way of weed control. So if we have a year we can have potatoes, and it's much easier to run the system with less herbicides. So it depends again on what your system is and what the right choice might be. And then are potatoes really that bad in terms of phosphorus? We already looked at it. So the last thing I wanted to show is going a little bit to the phosphorus debate. So this is the figure you already saw. We can see that the optimized system is really responding differently in this case. So in the nitrogen, we have the high fluctuation. Here we can see that phosphorus losses are stable and low for the optimized system. And a colleague of mine, he measured aggregate stability, and we can see that's very linked to aggregate stability in this case. So the things that are done in the system, which means cover crops, keeping the straw, but then having that 1 year, every 4th year, where there's a little bit of more soil working with the potatoes, actually does not affect aggregate stability too much. So phosphorus losses are very low. But it doesn't help for the nitrogen, it helps with the phosphorus. So when we're talking about phosphorus again, this is something to keep in mind. Some take-home messages is that I want to take away from you is that we have a lot of annual variation with these kind of experiments. It's important to look at not just 1 year, but at several years, and that we have those different nitrogen and phosphorus dynamics. Nitrogen has a higher variation and is very dependent on cover crop establishment as well, and the fertilizer and when it is given. Whereas the phosphorus is much more stable, and it really is linked to the soil stability that we establish in the soil. So that's sort of more of a long-term management measure that is needed, and it is important to look at the whole system. So what are the other implications in terms of weed management? What other implications do we want to, is it that we need to, do we have more aerial available? Do we want to reduce runoff, or do we have to produce a lot of food in a small area? So we need to, there's always a trade-off for everything that we do. And with that, thank you for your attention, and feel free to contact me.
Yes, I'm going to talk about measures for better nitrogen management at farm level. My slides will be in Norwegian, but I will speak in English. Analysis of nitrogen flows in agriculture indicates that there is a significant nitrogen surplus in Norwegian agriculture overall. And through crop production, the input of fertilizers and livestock farming, the purchase of concentrates and feed, other feeds, and the handling of manure within this system, we influences the nitrogen flows at most. And this have consequences for the climate and the aquatic environment, like Oslofjord. So I will present the measures from this NIBIO report, which was intended as a knowledge base for the development of an action plan for better nitrogen utilization in agriculture, conducted by the authorities. The report describes the measures at the farm level regarding their effect on nitrogen utilization and pollution, the ecosystem services. And I will go through the measures, which includes soil cultivation, cropping, mineral fertilizers or fertilization, livestock farming, and some mitigation measures. But I like to start with the soil cultivation and cropping because it is the basis for the nutrient management. The first at my list is to utilize the growing season by selecting species and varieties adapted to the local conditions and the climate. Here illustrated by the different crops' requirement for growing time or growing season, from the earliest to the latest varieties, as well as the expected growing time under unfavorable weather conditions, which may occur. Then it is important to provide the plants the best possible conditions for plant nutrient uptake by minimizing soil compaction, drainage, irrigation when needed, but excessive use can also cause nitrate leaching. Liming and plant protection is also important, and this can be summarized into good agronomy. The tillage strategies should aim to reduce the risk of nitrogen losses. Type of tillage and when doing the tillage is important, and this figure shows that more nitrogen is lost through leaching and runoff per unit area when plowing in the autumn compared to in the spring. In these cases, slightly more than a half kilo nitrogen per acre is lost, and it was at loamy or clay soils. So more can be lost on more sandy soils. If not needed in livestock farming, the straw should be kept at the field. It contains around 1 kilo nitrogen per acre. It has a high carbon to nitrogen ratio, which may also cause some immobilization and also then reduce nitrate leaching. The effect of using cover crops is well documented, especially for ryegrass and mixtures with other species and grasses. But there are a lot of different species and mixtures on the market, perennials and annuals, with different establishment times, and they can also, in a way, have different effects depending on the use and the species. And we must also not forget that they provide different ecosystem services. And an important point is that whether nitrogen fertilization can be reduced the following year, which is not always that clear in our research. Legumes can be used more. They are self-sufficient with nitrogen. In addition, they have valuable effect on the crop, in an arable crop rotation. But for example, should not be used in pure stand as a cover crop. Then I will go to the fertilization standards, if we can call it that are based on the Norwegian field trials over a long period under various conditions. The yield response of the different crops are more or less stable, but changes in goals related to product quality, profitability, or other environmental goals will impact the fertilization standards. They are presented in the so-called handbook and are implemented in the fertilization planning program. But an uncertainty is that the tools recommended depends on the expected yield. Producers of cash crops usually know their yield the yield level very well, while in grassland or forage production, more effort is required to determine the yield level. There is also grassland is the largest production in Norway, which also using most nitrogen per unit area. So there is a lot to gain from better nitrogen utilization. And NIBIO also offers some additional decision support tools related to fertilization. But there is a question regarding what happens in practice. We don't know to which extent the plants are used. In other words, how balanced the fertilization actually were. So there are some suggested measures to, in a way, record or write down the actual fertilization, or to use the average of, for example, the last 4-5 years to base or the expected yield based on these last 5 years. For example, in Denmark, they have to present their average yield and present that if it's higher than the norm, you can use or apply more nitrogen. Or we can start with a kind of nutrient account or a balance. Or we can also extend the use of the climate calculator. Split application of nitrogen fertilizer are commonly used in cereal production and at least recommended when using more than 10 kilo nitrogen per acre in total. It reduces the risk of nitrogen losses through leaching, but the effect depends on the weather conditions and the use or what is done in practice. By splitting the application, it is possible to stick more to what the plants can use. For example, if it's drought, it may increase in cereal production. It may increase the protein content, but you get more or less the same yield. It will reduce the workload in spring and reduce the risk of soil compaction. But in some cases, it may also have negative environmental impact. So the overall effect of these measures is not given, but it just reduces the risk of losses. By using technologies within the concept of precision agriculture, it is possible to have a kind of site-specific adaptation of fertilization to the plant's need, recognized by soil variation or the nitrogen status in the plants. This can be combined, or you can also just use steering assistance methods based on the use of global or GPS systems for precise driving on the field. Then you can avoid overlap or spreading outside the area. It can be used with or without this other approach. So the main consequence of this measure is saved fertilizer, or not, saved fertilizers through the use of the steering assistance, both in grassland and cereals. It is estimated just 2% yield increase, for example, in cereals, but the reduces on leaching losses can be about half kilo nitrogen per deca. So there is a need of investments, equipment, and the extent of this is not so big, but it's increasing. So to the livestock production. In livestock production, it is much about increasing nitrogen utilization from feed to the animal products. And the handling of manure, which is very related to ammonia losses. So then the importance is to to do something with the storage, increase storage capacity, and to have a kind of or environmentally friendly spreading. Feeding and optimization of the production is important, as well as reducing the forage or the waste, forage waste. So for the mitigation measures, it is important to underline that most of the N losses occurs through drainage. And the measures we use today have primarily effect on surface runoff. And then, of course, there have been much more focus on phosphorus losses than nitrogen losses. That's why it is like this. So the first measures is buffer zones. Unfertilized zones in grassland or grass-covered zones in field can consist of also other herbs or trees, and but natural buffer zones are the best in a way. But there is a huge variation in the effect. As you can see, it's just from 0 to 100 by measuring runoff of nitrogen. Then constructed wetlands, they are established in channels or small streams to optimize the kind of cleaning process through sedimentation, uptake in aquatic plants, and denitrification. So it reduces or had reduced the concentration by just not more than 70%. Then we have controlled drainage. That is to raise the water table to increase the loss of N2 to the air. And this is best suited for flat areas. So not so many areas will be suitable for this in Norway. Then we have this.
Randy, are you muted?
Yeah. Yeah.
We can't hear you more.
Oh.
We hear you online.
Oh.
Okay, now.
Do you hear me now?
No. Yes.
Okay. Should I just continue or should I?
We just lost you for 10 seconds.
Yeah.
Okay. Then I continue. Yes. Then I continue for restoration of wetlands. Nitrogen purification has a higher effect for these measures, around 40% for wetlands when it's tried in Denmark. So this is we are trying it under Norwegian conditions, I think, in some project. So to sum up in a way, measures that increases nitrogen efficiency are mainly a win-win for the farmer. Typically, losses increases when the yield curve flattens, as you can see here. So to sum up the measures that we think that can be useful is to have a continuous updating of the fertilization standards. You should stick to the plans of fertilization, split the fertilization, and use more of these precision equipment or precision agriculture equipment. Use of perennial cover crops, use of legumes, and no tillage in the autumn. But more knowledge is needed about the nitrogen efficiency of the various measures, as well as the development of effective mitigation measures for drainage water. So it starts with a good plan and a good agronomy that facilitates good plant growth, but there should be some room for adaptation during the growing season, for different weather conditions. And then it's important to recycle the organic resources at the farm. And in the end, we need to have some mitigation strategies. So then I just say thank you for your attention.
So I would like to use this opportunity maybe to make this the last presentation about the new EU project. I think I said something wrong in the morning. NIBIO is not leading, but we are leading one of the most important work packages. Maybe that's the correct way of saying this. But this project is about precision climate resilience for agriculture and forestry across the European boreal regions. And this is it is actually led by the Finnish Institute of Natural Resources, LUK. So basically, in this project, the aim is to produce more crops while losing less soil and nutrients, and also polluting less in the time of climate change. So as we all know that climate change is happening and it will continue, and this is challenging both crop production and environmental protection. And I just took this from a website. Is according to NVE, they wrote a very nice article about the drought and flooding situation in 2018 in many areas of Norway, and it said that there were 45 days with a flood warning in this year, and also there were very severe drought conditions, and there were 1,900 registered forest and grass fires just in the period of from January to August. So this really, this kind of extreme events really emphasize the importance of for us to think about the solutions for better agricultural and forestry adaptations to the climate change. So this project is funded by the Horizon Europe and the Mission for Climate Change, and it's quite a big project. It's 10 million euros for 4.5 years. It started this May and will last almost at the end of 2028. And the main aim of this this is a like innovation core, and the main aim of this project is to mobilize regions in testing solutions for climate resilience and also demonstrating transformative solutions to climate change. So just briefly about this, how this project is structured. So we have 7 different work packages, but the first work package is for the is to identify regional climate risks together with the regional actors, and based on interviews and workshops, and also the making risk maps for precipitation and temperature, etc. And the second work package is for working together with the regional actors for identifying co-design solutions for resilience. And there is a lot of work about modeling. And the third and the fourth work package, they are about to test and demonstrate agricultural and forestry demonstration solutions in practical ways. And we are actually leading the agricultural demonstrations, but NIBIO is also contributing to all of these work packages. And the fifth work package is about cooperation and co-creation of the solutions, again with the regional actors. And so in this project, is really stakeholders are very important. Like many of the people who are attending this seminar are very important actually for this work. And we also have dissemination and project management, etc. And specifically, NIBIO is working with Østfold County Council and Indre Østfold Kommune, and also for the forestry part, also Skogkurs in this project, and we NLR and also the Kanas and Shela agricultural high schools. They are not official partners for this project, but we believe that we will work also closely with them, because they are very important in this kind of work. And so for the agriculture part, we are planning to test and demonstrate the management practices related to catch crops, conservation tillage, specifically the reduce for avoiding the autumn tillage, and the soil improvers biochar and liming, that was also discussed in other presentations. And also there are drainage management component, and also about sedimentation ponds and opening river systems. So the main goal is to increase the crop and crop resilience to these different risk indicators related to climate change. And for the forestry, there are also about different measures. But as I don't work with the forestry, so I will skip that part. So here are just some examples of this, what we are going to do. So this project will be based on actually a lot on the past and existing research, and then we will also have some new research, of course. But for example, for the reduced autumn tillage and catch crops, and you can see from this photo, Mariana Beckman started this, for example, this runoff experiment at Chile about I think 15 years ago or something, and to evaluate the effects of autumn plowing, spring plowing, and winter wheat with autumn plowing, to evaluate their effects on nutrient losses and crop production. And also in the recent year, also the catch crop has been added as a new treatment to this field site. And so we are planning to include this site. And also in Norway, there have been I think about 15 field sites or something that have studied nutrient the effects of spring tillage and autumn tillage on nutrient losses in different parts of the country. And we in this work, we would also use some of the results from those kind of studies, and many of those studies were actually quite old. They were already from 20 years ago, and for the catch crop studies, we are planning to test this in the Østfold County and also Trøndelag. Yeah, and so in connection with the crop management for the soil improvers, I mean, Daniel has talked a lot about biochar. That's very interesting. But my feeling is that so far the Norwegian work has more focused on carbon. But for us who are more concerned about nutrient losses, so there may be a knowledge gap that we can help to fill in this project about the biochar effects on nutrient losses, and also structural liming is another idea that is in our mind. And then also we are including drainage management in this project, and Yannis has done a lot of work at this Grimsrud site at in the Østfold commune, and with testing different drainage systems effects on nutrient losses and soil losses. Yeah, so it's good that Yannis is allowing us to use some results from this site. And also for the sedimentation ponds, this kind of ponds have been used a lot, I think, in Norway for catching the sediments. But for many of these ponds, they are already very old and they need to be restored. And so we are still planning to include this kind of to have something about pond restoration, so that it could be something useful for the farmers. And also we are in discussion with the Indre Østfold commune about opening river systems. It seems that they have got permission to do for the opening river system, and hopefully this could be useful for reducing the erosion in the streams and in the surrounding areas. And we are in discussion about what NIBIO can, how we collaborate with this. And also we have also a task to develop a system level education demonstration tool in this project. So in my opinion, there are already a lot of results, like from past studies and ongoing studies, and also there will be results generated in different countries from this project. But then these results, when they are published in scientific papers or in other areas, maybe it's not very easy for the farmers to take in this information. So we proposed that to make a kind of a tool which is simple enough, but is very much focused on visualization, and to show the farmers, like maybe have a landscape map, and to show like if you use cover crop in this field, this kind of field with a high slope, it can be helpful to reduce nutrient losses, maybe by 50% or something. But if you are using it for landscape that is very flat, maybe it's not as effective as that. So we are aiming at to creating this kind of tool, and also we promise to develop a series of fact sheets and videos to document this different kind of practices. Yeah, and in the end, I would emphasize again that there are really many people that are involved from Norway for this project, and this is just a photo that was taken when we were in Helsinki for the kickoff meeting in May this year. But there are more people that that are involved, at least from NIBIO. Yeah, and with that, thanks for your attention, and yeah, and maybe the last session is for the concluding. Maybe I ask Theo to conclude.
Yeah, I think we have used a lot of time, so I make it quite short. So on behalf of the NJF, NJF is the Nordic Association of Agricultural Science, for the ones not knowing, who has been a co-organizer of this event. On behalf of the NJF, I would like to conclude the meeting. I think we have been through some really nice presentations. I think it was an interesting day, so I would like to thank all the presenters for their contributions. It's really nice to see that there are so many of you here on Teams that are interested in soil. Soil is an important resource. We have heard a lot about this today, not just because of its ecological function, also, or maybe especially in face of the climate change, but also due to its role for agricultural production. And the European community, they concluded with that soil degradation in Norway, mostly due to erosion, loss of organic material, but also soil compaction, is one of the most yield limiting vectors. So when it comes to soil, there are a lot of different, maybe conflicting interests. And it's really nice to see that there's an increasing focus on that. So I would like to thank all the participants today for their participation, for celebrating the World Soil Day. Last but not least, I would like to thank my colleagues in the organization committee. As I said, I think that was a nice event. So I would like to thank everybody and wish you a safe trip home. Maybe a Merry Christmas, because this is soon. And wie says,